And we can write a similar statement down for sine, and we're going to get a similar result. So sine of theta would be opposite over hypotenuse. So we would have, clearing the fractions out, that y would equal r times sine of theta. All right, now r in this picture is really coming from polar coordinates, but in this context, that's really the length of the vector v. So putting these facts together, this shows what we can write a vector out in terms of the components of the vector, I should say, x and y, come out to in terms of the magnitude and the angle theta. Notice theta is also always the angle from the positive x-axis. All right, so we're thinking about, and let's just add that to this picture here. We could think about adding an xy axis to this picture. Okay, and so theta is always going to be the angle from the positive x-axis. The x component is the length times cosine of theta. The y component is the length of the vector v times sine of that angle theta. Again, theta could be an acute angle as is pictured, or it could be an obtuse angle. All right, there's two other things I want to read off of this picture. I'm just going to note those for some work we're going to do later. I'm just going to put this off to the side here. If we use the Pythagorean theorem, we've seen from before what the magnitude of the vector is. That's not something new. The magnitude, if we solve for it, we get the square root of x squared plus y squared. So that's an important fact. The other one would be that tangent of the angle theta. Right? Sometimes we want to find the angle theta, and the way we do that is through the tangent function. Sometimes we're going to be given the x and y components, and we want to determine the angle. Tangent would be opposite over adjacent, so that's going to be y over x, and we can use that equation to sometimes determine angles from x and y if we're given x and y. So this is showing us two things. What we have in blue, if we're given the length and the angle, then we can write down the components. If we're given the components, we can go and determine the magnitude and the angle theta. All right, let's just get a little bit of practice working with the formula up above in blue. So suppose we're given a vector with magnitude 6 and direction 45 degrees. All right, let's write the vector down. So we want to write its components out. So it's going to be, again, putting in the magnitude. So in the formula up above, the magnitude is 6. So we're just going to put in 6, and then it's going to be times cosine of 45 degrees. And then it's going to be the magnitude in the y component is going to be the magnitude times sine of 45 degrees. All right, now these are known values to us. We know what the exact value is of cosine and sine of 45 degrees. It's the square root of 2 over 2. So we can substitute in those exact values. And then 2 divided into 6 gives us 3. So we could do that in each component and get a nice expression, a fairly nice expression. Each component, we would get 3 times the square root of 2 in both the x and the y component. All right, so there we go. All right, let's do the next one we've got listed. So again, for this vector here, let's call that vector, say, w. For part B, it's got magnitude 8, so that using the formula up above, it's the magnitude of the vector times the cosine of its angle. When we say the direction is 220 degrees, we mean the angle that vector makes with the positive x-axis is 220, and then sine 8 times sine of 220 degrees. All right, and now let's write that out. Okay, these values are also known ones. All right, so let's draw a quick picture to go along with this. We've got a vector 220 degrees, that's 60 past 180, so it's going to be 8 units long at an angle of 220 degrees. All right, now that's showing us that our vector, if we drew it in standard position, is in quadrant 3. So the x component and the y component would come out negative. All right, so the reference angle in this case would be 60 degrees. Cosine of 60 degrees is 1/2, but it has to be negative. We're in quadrant 3. So sine of 220 degrees is equal to negative sine of 60. Sine of 60 degrees is the square root of 3 over 2. Okay, it's got to come out negative though, because we're talking about a point or a vector in quadrant 3. All right, so to simplifying that, 2 goes into 8 4 times. So what we would end up with is the rectangular coordinates of this vector are negative 4 in the first component, -4 times the square root of 3 in the second component. So once again, what we've done here is we've applied the formula we derived. If we're given the length of the vector or its magnitude and the direction, we can write down the coordinates, sometimes referred to as the rectangular coordinates. All right. Last thing we're going to do in this video is talk about resultant forces. This is one application. If we have two forces acting on the same object, then the net effect is called the resultant force or the net force, and it's given just by the sum of the two. They combine together in that way, and we just do the vector addition. All right, so the resultant force is just all the forces acting on an object. This applies to two or more forces that we're going to do in the next example. So if you have, say, 5 forces, you'd add all 5 together if they're acting on the same object. All right, so we're going to wrap up with this example. It says 3 forces act on an object. They're given in rectangular coordinates. The coordinates of the vectors are given. We're supposed to find two things. We need to find the magnitude and the direction of the resultant force. So the first thing we need to do here is we need to add these vectors together. All right, so we're going to add just component-wise, -8 plus 0 plus 4. All right, if we add them together, we're going to get -4. -5 plus 1 is -4 plus -7 is -11. All right, so there's our resultant force. Let's compute its magnitude. So we're going to square the x component, square the y component, and then add them together. We'll get the square root of 16 plus 121 for a total of the square root of 137. Again, I'm just going to leave it in terms of that square root. We could compute that with a calculator, of course. All right, so that's the magnitude part. We've done half of the problem. Now we want to know what the direction of the resultant force is next. I've got this sketch started down here for us. So our resultant force came out to -4, -11. So let's sketch that vector. I'm just going to, again, eyeball it. We're going to go 4 to the left, 11 down. So it's looking something like this. There we go. All right, so that's our vector, capital F, the resultant force. The components were -4, -11. What we want to know is we computed the magnitude of that vector. We want to know this angle theta. All right. So when we say direction, unless specified otherwise, we're talking about the angle coming from the positive x-axis. We showed before that tangent of the angle theta will equal y over x. So for the angle we're talking about here, tangent of theta would be, the y component would be -11 over the x component, which is -4. The negatives cancel out. We get 11 over 4. All right, one solution of this equation, right, that trig equation has infinitely many solutions. One solution would be found, and I'm not even going to call that one theta because it's not the one we're looking for, but one solution is inverse tangent of -11 over 4. All right, so let's look at that. So arctangent or inverse tangent of 11 over 4. All right, if you work this out or plug this into a calculator in degree mode, this is approximately 70.01689 degrees to 5 decimal places. Now that's not quite right. Right? So again, there's infinitely many solutions. Our calculator is only going to tell us one using the inverse tangent keys, but inverse tangent gives us an angle between -π/4 and π/4, going back to the picture here, which means it's an angle in quadrant 1 or 4. So what this is really showing us, or what our calculator is giving us, is this angle in quadrant 1 that I just drew in green there. Well, we don't want that one. We want a half a revolution past that. We want to add pi radians or 180 degrees to that to get the angle pictured here. So sometimes we need to make an adjustment when we're using inverse tangent or any other inverse trig function to get us the appropriate angle. So the angle theta that we want is really going to be 180 degrees plus what our calculator was showing us. Okay, and if we do that, we're going to get that our angle theta is approximately 250.0689 degrees. All right, that looks better. All right, the angle drawn in blue, theta up above there, is in quadrant 3. It's got to be between 180 and 270, and we have that there. Okay, that's it for this recording.